morning, I'm Mauro Sadocco, Senior Product Manager in the field of air conditioning unit for data centers, telecommunications and high power density applications. In this video, I'll explain the guidelines and technical solutions offered by HiRef for climate control in environments, such as laboratories, clean room, archives and museums. That is, application where it is essential to maintain precise control of temperature and humidity. Before going into detail, I give you an overview of humidity, air, which form the basis for the concepts which I will present. Then I'll examine the specific characteristics of these applications and the checks required during the design phase, comparing them with operating limits. Lastly, it will be essential to configure the air conditioning unit with the right accessories to ensure accurate control of temperature and humidity in line with project specifications. Humidity air can be considered a binary mixture of idle gases, dry air and water vapor. Dry air itself is a mixture of gases with constant properties. Through psychrometry, it's possible to analyze the thermodynamic properties and transformations of humidity air within a system. The first parameter we analyze the dry bulb temperature. That is the temperature measured by a thermometer. This value is independent of a relative humidity and it is shown on the x-axis in the psychrometry chart. Another key parameter is specific humidity, which indicates the ratio between the amount of water vapor present in 1 kilogram of dry air and the total air mass. In the psychrometric chart, this is shown on the y-axis. Relative humidity is no less important. It expresses the ratio between the mass of water vapor contained in a volume of humidity air and the maximum amount of vapor that air can hold under saturation conditions at the same pressure and temperature. In the psychrometric chart, this quantity is represented by curves of relative humidity. The dew point temperature, on the other hand, is a key parameter for understanding the transformation processes of humidity air when humidity air is cooled to this temperature. Water vapor begins to condense as shown in this process. Let's look at an example of humidity air cooling without dehumidification, keeping specific humidity constant. Specifically, the transition from point A to point B represents air cooling in a coil heat exchanger, where a colder fluid absorbs heat from the air, since the coil temperature is above the dew point temperature R, the air does not reach saturation, and therefore condensation does not occur. This condition allows air to cool without altering the water vapor content, keeping specific humidity constant. The next transformation is critically important for the topic we are discussing, this cooling with dehumidification, followed by reheating. In this process, the air comes into contact with a surface at a temperature lower than the dew point temperature, causing both a drop in temperature, measurable as a sensible cooling, and a reduction in specific humidity, known as latent cooling. This process is shown in the diagram of humidity air represented by points A to B. It's important to note that the air outlet temperature will be adjusted through a reheating stage, which can be achieved using electrical resistances, hot gas reheat via an additional coil, or another supplementary hot water coil. The main effect of this transformation is a reduction in both the specific humidity and the air temperature. We have just seen the transformation used to reduce the specific humidity of air. But how can we increase the specific humidity? This can be done through steam humidification. This system is a type of humidification widely used in all environments where high hygiene standards are required, such as in medical environments. It works by distributing saturated steam directly into the air to be trapped, increasing humidity through what is essentially an isothermal transformation, shown in the psychrometric diagram as the A-B transformation. This was the final measured transformation of humidity air. Now let's go into the application details. Air conditioning laboratories, clean rooms, archives and museums typically share the following features: low or almost zero internal heat load, a need for precise control of temperature and relative humidity, small spaces to be treated, and in some cases the presence of fresh air intake flows. In some cases the space may be occupied most of the time. Given the common characteristics, the following outlines the checks required to evaluate a proposed solution with HiRef air conditioning. So check the set point values for temperature and humidity to be controlled to see if they fall within the acceptable operating limits we will discuss. Minimum tolerance required for temperature as well as for the relative humidity to be controlled. And also, last but not least, check the type of cooling, whether it's total recirculation or with outdoor exchange aeration, and the presence of any people inside the room to be treated. As mentioned, the first check consists in verifying that the temperature and humidity values are within the acceptable operating limits shown in the following diagram. So temperature from 18 to 35 degrees relative humidity, maximum 65% and specific humidity, maximum 20 grams per kilogram of dry air. Operating condition for indoor air dehumidification, minimum dew point of temperature of 5 degrees. So all these parameters define this area, in blue within the psychrometric charge. As for tolerance, minimum tolerance plus or minus 5% of relative humidity under steady state conditions, that is in the absence of variation in thermal load. So if, for example, I have set point value of 65%, it means the range will be between 60 and 70%. Minimum tolerance for temperature plus or minus 0.5 degrees for temperature, that is the return air temperature again under steady state conditions. No variation in thermal load. Check the operating limits. It is necessary to verify if there are contributions of outside air. This implies sensible load and additional latent load in summer. Requirement for humidification and heating in winter. So these aspects must be considered when defining additional loads. These aspects must be considered when determining the size of the cooling units. Therefore, the minimum data required for verification are airflow of fresh air intake in cubic meter per hour, temperature and relative humidity, maximum values of outdoor air under summer conditions. These data define the sensible and latent power that must be provided to maintain the required set point. Temperature and relative humidity, minimum values of outdoor air under winter conditions. These data therefore define the requirement humidification capacity in kilogram per hour and the heating power in kilowatts needed to maintain the required set point. Once the boundary conditions are defined, it is necessary to determine the best type of installation, depending on whether the environment is attended or not. In the case of an unattended environment, the air conditioning unit is installed inside the space to be conditioned. Below you can see an example of air conditioning units with air intake from the front and upward air supply. An additional 25 cm base is required in the absence of a raised floor to allow connection for the dehumidifier hydraulic lines. In the case of an attended environment, it is recommended to install the air conditioning unit outside in a technical room. Air return and supply can be managed using a plenum and a 50 cm high base. Once the best solution is defined, we will now define the configuration, strongly recommended for this type of application. The first required option is the dehumidifier plus humidify option. The unit is equipped with a combined temperature and humidity sensor for controlling these parameters at the air intake. The dehumidification function first allows for a reduction in airflow in the presence of high humidity and simultaneously forces the compressor to operate in case of direct expansion units. In the case of chilled water units, it forces to the complete opening of the water valve. These effects are intended to reduce as much as possible the temperature of the coil fins, so that it operates below the dew point temperature, to allow air dehumidification and condensation formation. In the opposite case, steam is released into the air when the humidity value is below. The set point using the humidifier with immersed electrodes provided in the HiRef air conditioner. It is important to pay attention to the characteristics of the humidifier supply water, comparing them with the specification indicated in the manuals. If these characteristics are found to be incompatible, there is an available version of the humidifier with electric titanium resistance, which can be installed externally to the air conditioner. This model of humidifier will therefore be controlled by the air conditioner, while a steam lance will be provided, installed on the side panel of the air conditioning unit for the diffusion of steam inside the unit. As seen previously, to control the temperature during the dehumidification process, a post-heating system is also needed. Heating may be required during winter operation. Several options are available for post-heating and heating in the HiRef air conditioning unit. For example, a hot gas rate coil in the hot gas coil post-heating option. There is an additional finite coil after the evaporating coil. A three-way modulating valve regulates the bypass of the gas from the compressor discharge to maintain the air temperature set point during the dehumidification operation. This system reduces about 90% of the total cooling capacity when combined with electrical heaters. The precise hot gas coil takes priority over electrical heaters. Electrical heaters are a simple system used for heating and post-heating, available with a different management systems, single-stage resistance or multi-stage with the 2 or 3 steps, or finally modulating with a continuous regulation. It is recommended to use modulated electrical heater for this type of application. It should be noted that the heating power is about 70% of the total cooling capacity, so it is not possible to offset more of the cooling power. Upon request, it is possible to provide electrical pre-arrangement to control external duct-mounted electrical heater modules, which are then managed by the air conditioning units. In this way, it is possible to achieve higher heating capacities. If hot water is available at the installation site, the air conditioner can be equipped with an additional coil and a three-way regulation valve, which can be used for both heating and post-heating and can be combined with electrical heaters. The hot water coil has priority over electrical heaters. In addition to the minimum required configuration, another factor to consider in a direct expansion air conditioning solution is the type of compressor. For this application, it is strongly recommended to use a brushless inverter modulating compressor from the energy range. In this final slide, I would like to summarize the key points regarding this application where precise temperature and humidity control is required. Below are the fundamental points. Check if the required temperature, humidity and tolerance are within the acceptable limits of operation for HiRef air conditioning units. Check whether these are any contribution of outdoor air and therefore assesses the volumes and condition of outdoor air in the summer and in the winter to determine the required additional loads. Check whether the environment is attending or not to suggest the most appropriate type of installation. Configure the unit with minimum accessories, that is, dehumidification plus humidification, post-heating with a precise hot gas, or with hot water coil, hot water heating, or external duct-mounted electrical heaters. I remain available for any further clarification or request regarding this type of application. Thank you for your attention and see you in the next video.